For those of you building agents, you know the dirty secret, right? Your model might completely crush a simulated sandbox benchmark, but the second it hits like a random modal Wi-Fi pop-up on a real phone, it just completely breaks.
Oh yeah, the sim to real gap. It is the ultimate bottleneck right now.
Exactly. So today on AI Paperslop, we are doing a deep dive into the Qwen-UI-Agent technical report. That's toward next-generation real-world centric foundation GUI agents released by the MAI/UI team at Alibaba Group on July 31st, 2026.
Right, and we've got a lot of ground to cover with this one.
We do. So here is the 60-second download on why this matters to you. The researchers completely abandoned pure sandbox overfitting. Instead, they built this hybrid GUI command line and API action space, and they hooked it up to a massive cluster of over 100 physical, real-world phones.
Which is just a wild scale for physical infra.
It really is. And to train it, they engineered an auto-research data flywheel and used group relative policy optimization, or GRPO, running online reinforcement learning on trajectories exceeding 100 steps.
Long horizon stuff.
Yeah. And the result is a staggering 92.2% on the mobile world real benchmark. That absolutely destroys frontier models like GPT 5.6 Sol, Claude Opus 4.8, and Gemini 3.1 Pro.
The broader takeaway here for the ML engineers listening is that this paper, it provides a concrete architectural blueprint. We're finally moving past the era of just juicing benchmark numbers in sterile environment.
Right. It's about real-world usability now.
Exactly. What Alibaba built is a system for proactive cross-platform agents that actually verify their own work under, real-world conditions.
Let's start with those real-world conditions, because understanding how Qwen-UI-Agent hit that 92.2% success rate really requires looking at why previous models failed so spectacularly.
Oh, the failure analysis, this paper is fascinating.
Yeah, when they tested models like Qwen 3.7 Plus on physical devices, the failure breakdown was incredibly revealing. Like 52% of the failures were caused by real-world UI chaos.
Chaos is definitely the right word for it. I mean, sandbox benchmarks give you this perfectly clean state. But the real world gives you unexpected ad paywalls, or KPCHAs, or heavily stateful pages where the visual semantics change dynamically based on, network latency.
And the frontier models just panicked.
Yeah, they simply misread those states.
Yeah.
And then you have the other 40.3% of failures, which stem from execution capability limits.
It's a memory decay issue, right?
Exactly. A model gets, say, 20 steps into a deep UI tree, loses track of the context window, and literally forgets the state of the task it was trying to accomplish.
So a sanitized simulator just doesn't prepare a model for the density of a modern mobile ecosystem. To bridge that sim-to-real gap, they built this massive physical infrastructure.
The 100 physical phones.
Right. They wired up over 100 physical phones supporting more than 150 live applications. And these had active network connections and real account states. But they didn't just buy a one-to-one ratio of phones to agent sessions. They used this virtual screen mechanism.
Yeah, they drastically scaled throughput by running multiple independent app sessions concurrently on a single physical phone's kernel.
How does that even work at the OS level?
So the Android Surface Flinger is basically rendering multiple isolated virtual displays simultaneously. This allows them to maximize the hardware utilization of the physical system on a chip.
Oh, wow.
Yeah, and they do it without sacrificing the authenticity of the real-world operating system layer.
It is essentially Kubernetes, but for physical phone screens. You are treating bare metal mobile devices like ephemeral cloud compute.
That's a great way to think about it.
But managing ephemeral compute at that scale requires a serious orchestrator, because physical phones, they drop off the Wi-Fi, applications crash, testing accounts get rate limited by real servers.
It's a logistical nightmare.
It is. So they introduced a health-aware scheduler that dynamically routes tasks. If a device throws a system error, it just gets put on a dynamic blacklist until it is repaired.
Which is super necessary.
Oh, wait, I have to challenge the methodology here regarding how they evaluate those failures. Like, if an agent is running a 50-step task and fails at step 40, how do the researchers definitively prove that the target app genuinely crashed versus the agent just hallucinating a broken UI state and failing the task itself? Because VLMs hallucinate all the time.
You've hit on the exact reinforcement learning alignment problem they had to solve there. You cannot penalize the model's policy if the target server went down.
Right. That's not the model's fault.
But you also can't let the model make excuses for poor navigation.
Uh-huh.
So their solution was implementing a VLM acting as an auto-judge. But it doesn't just look at screenshots.
What else is it looking at?
It actually correlates the visual frame diffs with the actual runtime system logs from the device.
Oh, so it is cross-referencing the model's output with the operating system's ground truth.
Precisely. If the model issues a tap coordinate and the visual state doesn't change, the VLM auto-judge checks the system logs.
Clever.
Yeah, and if the logs show the application through a null pointer exception or a network timeout, the judge flags it as an environment failure, not a model failure.
So the model doesn't get penalized.
Exactly. The trajectory is cleansed from the penalty phase. Only trajectories validated against both visual state and system state are kept for training.
That level of validation is so necessary when you scale up. And speaking of scale, supplementing those 100 physical phones, they built an additional 10,000 concurrent simulated sandboxes.
Simulated cluster, yeah.
But what really caught my eye is that they didn't spin up traditional Android emulators for this. They rebuilt the mobile world environment using Redroid.
Right, because standard emulators rely on QEMU, or nested KVM hardware virtualization, which introduces just massive overhead.
Right, you are simulating the entire hardware stack.
Exactly, which bloats memory and completely destroys CPU efficiency.
Which means you could never run 10,000 concurrent environments without just a bankrupting compute budget.
Absolutely not. So Redroid bypasses that entirely. It runs Android as a container directly on the host Linux kernel using standard C groups and namespaces.
Wow, so no emulation overhead.
Right, it strips away the virtualization bottleneck. This architectural choice is what gives them the sheer volume needed for broad trajectory collection, while that physical cluster acts as the anchor to ground the policy in reality.
It's a brilliant setup, but having a massive physical and simulated cluster exposes a secondary bottleneck, right? Computational friction.
Oh, the action space problem.
Yeah. If you force an LLM to interact with these devices using only a graphical interface, you are artificially handicapping it. Pure GUI interaction is way too slow for system-level tasks.
A fundamental tension in agent design has literally always been the action space.
Yeah.
If you restrict an agent to pure GUI, you force it to operate exactly like a human dragging a finger across glass.
That's just terribly slow.
Yeah, it's a highly inefficient modality for a machine.
See, I used to argue that the whole point of a GUI agent was to navigate visual interfaces, so command line interfaces were basically cheating. But when you think about the inference costs, it's just absurd.
It makes no sense at scale.
Right. Imagine forcing an LLM to visually drag a cursor to open a terminal app, type a bash script letter by letter, and then try to read the raw text output rendered as pixels on a screen.
You burn massive amounts of inference tokens and drastically increase the probability of an execution error at every single step.
So to fix this, Qwen-UI-Agent uses a highly expressive hybrid action space. It outputs standard GUI actions, like click, swipe, and type, but it can also output CLI actions to execute bash commands directly.
And it can make direct API calls.
Exactly. And on top of that, it includes an excuser control action.
Which I think is one of the most important additions.
Yeah, the excuser action functions as this ultimate fallback for sensitive operations. If the agent hits a payment gateway or triggers a two-factor authentication prompt,
or encounters a CAPTCHA, it is not confident in solving.
Right. It doesn't just guess and hallucinate a destructive response. It literally pauses the trajectory and prompts the human user for input.
But integrating this hybrid action space required redesigning the observation space too.
Right. How did they handle that?
Well, in their Alice World computer use environment, which runs an Ubuntu virtual machine, the model doesn't just get a screenshot after every action. If the agent executes a CLI command, the standard output, standard error, and exit status are returned simultaneously alongside the post-action visual screenshot.
So it's getting visual and programmatic feedback at the exact same time?
Yes. The model reasons over the visual interface state and the programmatic execution feedback in the exact same forward pass.
Which naturally leads to one of the most efficient mechanisms in the whole paper-batched actions, because the model is not constrained to outputting a single action per turn.
This is huge for inference speed. Whenever the model determines it does not need immediate environment feedback to proceed, it outputs an ordered sequence of actions all at once.
So if it needs to type a 12-character string and press enter, it doesn't need a visual frame update after every single keystroke.
Exactly. In the computer use benchmarks they ran, over 40% of the action outputs are actually batched.
40%. That cuts out a massive chunk of inference overhead. It compresses the trajectory length entirely, making like a 100-step logical task look like a 40-step execution task to the model.
It's incredibly efficient.
But even with a highly optimized action space, training a model to generalize across 150 real-world applications introduces a data curation nightmare.
Oh, the human annotation problem.
Yeah, human annotation simply does not scale here. You cannot hire enough engineers to manually click through every single edge case and pop-up in the Chinese mobile ecosystem.
You'd need an army of annotators. So that bottleneck forced them to implement an auto-research-style data flywheel, essentially automating the entire capability acquisition pipeline.
How does the flywheel work in practice?
Strong foundation models are deployed to synthesize the tasks, configure the initial environment states in the containers, and crucially, write the state-based verifiers that determine if the task actually succeeded.
Okay, but the handling of the rollout data is where this gets brilliant for me. Specifically, their step-level VLM as judge for supervised fine-tuning, or SFT.
Yeah, this is a major departure from traditional RL.
Right, because in traditional RL paradigms, if an agent runs an 80-step trajectory and fails the verifier at step 79, the reward is 0. The entire trajectory is discarded.
Which is terrible.
Yeah.
Throwing away 78 perfect steps of execution is just a catastrophic waste of learning signal.
Completely.
So instead, the Alibaba team uses a VLM to evaluate failed runs step by step. They do this to extract what they call the maximal contiguous correct steps.
So those first 78 actions are isolated, verified, and retained for the SFT corpus.
Exactly.
It is exactly like a compiler that saves your code base up to the precise line where a syntax error occurs. Rather than wiping your entire hard drive because you missed a semicolon, you extract every possible drop of optimization from a failed rollout.
That's a great analogy. And furthermore, they capture reflection steps.
What does that mean in this context?
So if the model makes a mistake, recognizes the discrepancy in the next visual frame, and takes a corrective action to recover, that sequence is preserved in the training data.
Oh, so the model is explicitly trained on how to recover from its own errors.
Yes, while the noisy, irrecoverable branches are pruned out.
That is so smart. But aggressive fine-tuning on specialized GUI tasks carries a major risk, right? Catastrophic forgetting.
The classic problem with fine-tuning.
Yeah, you do not want your foundation agent to suddenly forget how to write Python code or do basic algebra just because it spent a week heavily optimizing its weights for navigating a flight booking application.
Right. To stabilize the model, they mix general capability data into the SFT process. And the critical insight here is the specific distribution of that data. They use in-distribution data.
Meaning stuff the model already knows.
Exactly. They take a broad pool of math, coding, and general QA prompts, have the base model generate responses, verify the correct ones, and inject those into the training mix.
See, the paper makes a very specific point that using out-of-distribution data, meaning challenging mathematical or coding examples that the base model currently fails on, actually degrades the GUI training process.
It does. Out-of-distribution data introduces competing optimization gradients. The loss function just gets pulled in completely different directions.
Right, because you're trying to teach the network entirely new, complex reasoning structures while simultaneously trying to teach it nuanced UI navigation.
The gradients, conflict, and performance in both domains suffers. But by using in-distribution data, you rehearse established capabilities to anchor the baseline weights.
Which allows the new optimization to focus purely on the agentic tasks.
Exactly.
So that mechanism anchors the model perfectly. Supervised fine-tuning provides these strong base competencies. But as you mentioned earlier, GUI tasks are incredibly long horizon.
Yeah, sometimes well over 100 steps.
Right. And when you cross 100 steps, you face the problem of compounding errors.
Right.
One slight misclick at step 40, and the SFT model has no idea how to recover by step 60. To solve that long horizon drift, they applied online reinforcement learning.
And this is the phase where that Redroid infrastructure really pays dividends. They rolled out a tailored variant of Group Relative Policy Optimization, or GRPO, across those 10,000 concurrent sandboxes.
Why GRPO over standard PPO?
Because standard PPO requires a massive value model, often the same size as the actor model, to evaluate the states. When you're running 10,000 parallel environments, the memory footprint of a secondary value model is just prohibitive.
You'd run out of VRAM immediately.
Exactly. GRPO drops the value model entirely. It samples a group of outputs for the same prompt and normalizes the rewards relative to that specific group, making it vastly more memory efficient for this kind of scale.
And to make GRPO effective, you have to feed it the right curriculum, right?
Yeah.
They use a model adaptive curriculum that continuously tracks the policy's success rate on specific task clusters.
Right.
It drops tasks where the model has a 100% success rate because, well, there is no learning signal left to extract. And it also drops tasks with a 0% success rate where the model is just flailing.
It heavily prioritizes tasks with intermediate success rates. That's the exact frontier of the model's learning capabilities.
So the result of this RL phase generated two highly distinct emergent behaviors that were never explicitly programmed into the loss function, which I found amazing. The first is verified completion.
Yeah, this one is great. Before reinforcement learning, the SFT model would execute a script, see that the script finished executing without an error code, and immediately output a termination signal, assuming the task was successful.
Oh man, every ML engineer has lived that nightmare. The code compiled, so the feature must be working perfectly in production.
Exactly. The paper highlights this LibreOffice workflow to demonstrate it. The SFT policy runs a script to generate a clustered chart. The script check passes, so the agent terminates.
But it didn't actually check the output.
Right. It never looked at the output, and it ended up shipping an empty chart with no data series. But after online RL, the agent organically learns to open the GUI to double-check its own work. Yeah, in the same LibreOffice scenario, the RL agent reopens a file, visually inspects the result, and discovers a leftover crash recovery dialog blocking the chart rendering.
So what does it do?
It autonomously force kills the recovery instance, clears the entry, and visually verifies the chart is rendered before signaling task completion.
That emergent verification behavior dropped the false stop rate, where the agent declares success but actually failed by 11.2%. It literally learned paranoia.
It's incredible.
And the second emergent behavior is even more fascinating. They call it bash as hands, GUI as eyes. The model organically evolves a cross-modal collaboration strategy.
During the RL exploration phase, the policy figures out the most computationally efficient way to leverage its hybrid action space.
Meaning it stops trying to click through menus for everything.
Right. It learns to use rapid CLI commands to execute state changes, like moving files, altering system settings, or querying databases, because bash is vastly faster and more precise.
And then what?
Then, it immediately switches to GUI actions to visually inspect the results of the terminal command in the actual application interface.
What blows my mind is that the loss function was simply complete the task. The reward signal naturally pushed the RL agent to evolve the exact same workflow a human systems engineer uses when debugging a remote server.
It's convergent evolution.
Exactly. You run a grep command to change a config file, and then you open the web interface to visually confirm the site is back online. The policy converged on human engineering best practices purely through reward optimization.
It is a highly efficient execution pattern that only materializes because the infrastructure, the hybrid action space, and the GRPO algorithm provide the freedom for it to emerge.
It's so cool. So Qwen-UI-Agent now possesses the physical infrastructure, the hybrid action space, the automated data flywheel, and the GRPO optimization.
All the pieces are there.
Right. But a reactive sandbox bot waiting for a prompt is basically useless in the real world. To fix that, the researchers built a harness layer to transform it into a proactive assistant, operating continuously across platform boundaries.
The harness layer elevates the agent from just a benchmark curiosity to an actual real-world utility. It allows the agent to run continuously in the background across mobile, computer, web, and their deep search environment.
And it maintains context across all of them.
Yes. It preserves the context and the memory state as the workflow jumps seamlessly from, say, your phone to your desktop.
The flight cancellation workflow in the paper illustrates the power of this perfectly. A flight cancellation notification hits the user's mobile phone. The agent's harness layer perceives this proactively, like you didn't open an app and ask it to look.
Right, it's always watching.
It reads the notification, identifies the affected itinerary, and then uses DeepSearch via API to find alternative flights.
And DeepSearch functions as this latent reasoning step. It acts as the agent's knowledge retrieval brain before it starts blindly clicking around a visual app.
Which saves so much time.
Exactly. The researchers highlight another example for this. Finding the biggest comeback in the World Cup. Instead of opening a social media app and randomly querying the search bar, the agent uses DeepSearch first to pinpoint that the answer is the Argentina 3-2 match.
No, that makes sense.
Yeah, and only then does it navigate directly to that specific video on the Rednote app. It separates knowledge retrieval from visual navigation.
So back to our canceled flight. It uses DeepSearch to find the optimal new flights. Then it uses the mobile GUI to trigger the accuser action.
That crucial safety step.
Right. It pops up on your screen asking for explicit approval to rebook. The moment you approve, it books the flight. Then it seamlessly jumps to the computer environment.
Cross-platform execution.
Exactly. It uses CLI and GUI actions on your desktop operating system to update a local Excel meeting schedule impacted by the delay and drafts an email to your team with the updated spreadsheet attached.
It executes an end-to-end cross-platform workflow triggered by a single mobile notification. And the benchmark results validate this architecture completely.
Let's hear the numbers.
On Osworld verified for computer use, it achieved 79.5%, beating Gemini 3.1 Pro and Seed 2.1 Pro. On Web Arena for browser use, it hit 73.6%. And for pure GUI grounding on ScreenSpot Pro, it secures 81.5%.
Those are massive jumps. But we have to address the obvious security implications here. An autonomous agent running constantly in the background, reading every push notification, and holding the execution privileges to operate your desktop file system is a terrifying prospect if it hallucinates.
Oh, it's the defining security challenge for foundation agents. And it underscores why that accuser action is structurally vital.
It's not just a convenience feature.
No, it serves as a hard safety valve integrated directly into the action space. The agent is capable of perceiving the problem and drafting the entire multi-step solution, but the RL policy is explicitly trained to pause and require human cryptographic handoff before executing consequential operations.
Like authorizing payments or modifying local file systems.
Exactly. The model's capabilities are vast, but they are architecturally constrained by human authorization loops.
Which is exactly how it should be. For the ML engineers and researchers listening to this deep dive, Qwen-UI-Agent proves that the sim-to-real gap is solvable.
It really does.
If you combine scalable compute on real-world physical devices with GRPO and a hybrid GUI CLI action space, you can build an agent that navigates the chaos of the real world. Pure sandbox training is just a dead end for real-world reliability.
You cannot optimize for the real world without exposing the policy to the unpredictability of actual applications.
Yeah.
And you have to give it an action space expressive enough to navigate that unpredictability efficiently.
Completely agree. I want to leave you with a structural question about the future of the software industry to think about.
Oh, I like where this is going.
For the last 2 decades, the tech sector has spent billions of dollars building, maintaining, and securing a dedicated REST APIs just so software could talk to other software.
Right.
But if foundation models like Qwen-UI-Agent can perfectly navigate human GUIs, handle unpredictable pop-ups, and read visual states better than any traditional scraper, is the era of building dedicated REST APIs coming to an end?
That is a massive question.
If the graphical user interface is universally readable and operable by AI, well, maybe the GUI itself is the ultimate API.